Hello, and welcome to the first video for section 15.2. Now the big picture here in chapter 15, right? In 15.1 we introduced functions of two or more variables, what their graphs look like, how we can understand them better. In this section we're going to build up limits and continuity, and just like we did in Calc 1 after limits and continuity, then we can start to talk about derivatives. So what we're building up to is being able to use calculus on these functions of several variables. In chapter 15, we're going to stick to differentiation, and then chapter 16, we'll get into integration of these things. So in this video, we're introducing limits for functions of several variables. So in order to do this effectively, we need to jump back. Jump back to calculus 1 to functions of a single variable. So just think of functions like f of x. And remember what a limit meant there. Right, remember that we say, I'll say limit as x approaches a. So this is for a real variable a, or a real number a. Limit as x approaches a of f of x is equal to L if for all epsilon, and so I'm going to give you the rigorous definition first. I'll remind you of this rigorous definition if you even encountered it in Calc 1, and then we'll talk through what it means so we can understand it at a higher level in more dimensions. So limit as x approaches a of f of x is equal to L if for all epsilon greater than 0 there exists delta greater than 0 such that if x is within delta units of a, then f of x, our outputs, are within epsilon units of L. Right, so the idea is this part of it, down here, it's saying we can make our function, we're saying the limit is L, so that means the function values are approaching L as x approaches a if we can make f of x as close as we like to L, as close as we need to L. And how close do you need to be to L? Arbitrarily close. You get to pick the epsilon. Some antagonist can give me any epsilon, any smallness, any closeness to L, and I can find a delta such that if x is close enough, that amount of distance from A, then f of x is within epsilon units of L. So can make x close enough to A in order to ensure that f of x is as close as necessary to L. That's the idea. But I'll give you another interpretation of this, and this is usually, remember what, one second. Yeah, what exactly is this saying? One way to think about this is, notice that these are distances here. What this is saying is that if we approach A from any direction, since we're in since we're in one dimension here along the axis, the only directions we can come from are from the left and the right. So if we approach A, I'll use this color for this. If we approach A from either the left or the right, and we track the function values as we do that. So let's say we approach from the right. That's what our track looks like as function values. That track approaches L. Those function values approach L. And if we come from the left, those function values also approach L. Right? This is in the familiar theorem, limit as x approaches A of f of x is equal to L if and only if limit as x approaches A from the left of f of x is equal to L, and limit x approaches A from the right of f of x is equal to L. Right, this was a really useful way to think about limits, is that we needed to be able to approach from the left, from the right, in order to prove that the two-sided limit exists. Of course, two sides, because we only have one dimension to travel in along the x-axis. So, all right, So this is what it means to be a limit for a function of a single variable. We want to extend this now to functions of two variables. So think about what's changed. Our domain is no longer just going to be an axis, right? Our domain is some region in the xy plane, and then our function is going to be hanging above that. So we're going to have to extend this idea of approaching our limit, approaching a, and then extend our idea of moving along the function. All right, so here's our definition for a function, for limits of functions of two variables. So here we're using, again, the limit L. L is, again, a real number. And P of xy, this is not a function, this is a variable point. In the xy plane. And this is a fixed point. This is like our a from the last definition for a function of a single variable. So for this, you can think the value a from the last one. But now it's ab because we're in the xy plane. Right, we're approaching a point in the xy plane. And so our limit notation looks a little bit different, right? Limit as this variable point xy approaches the fixed point ab. So this is a limit as we go to ab of f of xy. We could also write this as limit as p goes to p naught if we want to be a little bit fancier and have these names associated with them. That's equal to L, all right? So this is our definition for that limit being equal to L. So again, have this picture in your mind of traveling in the domain towards the point p naught, and then the function values need to be approaching L. So how do we make that really rigid? Excuse me. Here's our epsilon again. This is our closeness to L. There exists a delta. This is, we need to make our point xy close enough to AB in order to ensure that f of xy is close enough to L. So that's the idea. But now we're in two dimensions in the domain, and so we need a two-dimensional distance, and so you can recognize the distance formula here. So again, this is, we can make P our variable point, or I'll say not as close, close enough to our fixed point AB by, so yeah, we can make this close enough to ensure that f of xy is as close as we want, or as close as we need to L. So this part of the definition actually looks the same as with a function of one variable, right? Because our function outputs are still just along an axis. They're still just real numbers and not points. But here, this is a little bit different in the domain because our variable is now a point in the xy plane, right? And so now we have the distance formula between our variable point and our fixed point that we're approaching. Okay, so what exactly, we need a visual to go along with this. And I don't want to draw it, so I'm going to jump to a interactive figure here in our textbook. So this is the idea. Here I have this function is in yellow here. That gold, that's our function, right? It looks like a surface in R3. Here's our domain down here in the xy plane. The red bit here is not necessarily the domain, but rather this disk around our fixed point AB, right? So we're considering all possible points that are within a certain distance from our fixed point AB. And so thinking back to that definition, right? Okay, so here's our limit L. This is what we're claiming the function is approaching as we approach this fixed point P naught, right? So what that formal definition is saying is, let's say you tell me make the function value within 1 unit of L. I'll say, okay, let me do some calculations. I'll find out that in order to make my function values that close to L, within 1 of L, I need to make my delta this small. So I need to make this little disk down here, the distance from this fixed point, small enough so that all of the function values, if you notice, all the function values are between those two green planes that represent L plus epsilon and L minus epsilon. Right? So all my function values then, if I select this disk around P naught, all the function values that correspond to that fall between L plus epsilon and L minus epsilon. And what the definition is saying is no matter what epsilon I'm given, I can do that. That's what it means for the function of two variables to have this as its limit point as we approach P naught. So for instance, if you say 0.5, okay, I have to do my calculations again, and I say, okay, here's delta for that. You need to make it this close to P naught, and then if you do that, all of the function values that are within that many units of P naught will be within epsilon units of L. Right, so as I change this epsilon, I'm bringing these green planes closer together. As I decrease epsilon, it gets it closer together. And that's going to mean I need to get closer and closer to P naught. And that's why this is the definition, because I can kind of sandwich that point. That's the idea, is I can keep getting closer and closer to P naught in order to make f of x as close as I want to L. And that's what it means to be a limit for functions of two variables. All right, let me jump back to the blackboard here. That's sort of what this means, but that's our rigorous formal definition. We're not going to actually use that too much to calculate limits. Just like we didn't use it that much in Calculus 1, and depending on your structure, you might not have even been introduced to it, and that's okay. This might be the first time you're hearing about this sort of an idea of what a limit is. But this is what mathematicians use as the definition of a limit. But just like with one variable functions, there was this other idea to it. Let me jump back up to that again. There was this really nice theorem here that said the limit exists if and only if both of the one-sided limits exist and are also equal to L. Right? As we approached A, our fixed point in the domain, from both sides, our function values approached L. Now, we're in a two-dimensional domain rather than a one-dimensional domain, right? So here we are, this is our domain down here. Now I can approach this xy, so treat this xy, or maybe I'll call this x naught, y naught. Let me fix that a little bit, x naught, y naught. We'll call this my fixed point P naught. We can approach that, say, from the positive x direction, right? That's one way to approach that fixed point. I can approach from the other direction along the x-axis, and then I can look up and see, oh, if I do that, if I approach from the positive x direction, my function values will look like this. So that's me tracing out the curves there, and they approach my limit point. So let's call this L here. They approach the limit point L. As I go from this side, so maybe that looks like something like this, something like that. Those also approach L. But there's other ways I can go, right? I can go along the y-axis and approach P naught. And then maybe my function values will look something like this. But those also approach L. But I needn't stop there. I could do sort of any combination of these. I could approach from a diagonal way. And I need to check and make sure my function values approach L along that line or along this line. So I can come at this thing from any sort of curve. Any curve that goes through this point, I can approach the point from that curve. And that gives me a different set of function values that have to approach L there. So I can't, like in the one-dimensional version, I just had two limits to check. The problem here in 2 dimensions, the two-dimensional domain, is that there's an infinite number of ways I can approach this point. And so that's a problem. So there's not just 2 things to check anymore, there's an infinite number of things to check. Right? I could approach, maybe there's a parabola here. I could approach along a parabola, and then I could look at my function values here and see, did they approach L along that parabola? So there's limitless, literally an infinite number of possibilities here, so we can't necessarily check all the different paths like we could do in in Calc 1, we couldn't check both of the, we could check both of the limits there because there were just two of them. Here we have an infinite number. We can't check all of them. So this isn't a good way to prove that a limit exists. So this doesn't really help us prove that a limit exists. All right, wait, let me write this down a second. That the limit as f approaches p naught is L if and only if the function values along all paths p naught. So that's what I'm describing here, is this. But this works best in the contrapositive. That is, if I can show that there are two paths. So if there are two paths, maybe let me write this somewhere else. Write it down here. I'll say so. We can prove a limit does not exist if we can find at least two paths that yield different limits. Yeah, maybe that's not super exact language, but that's the idea. This is our main method for showing a limit does not exist, is to find two separate paths for which the function values do not agree, that yield different limits. All right. So we still haven't gotten to like how do we actually determine what the limit of a function is? How do we actually compute a limit of a function? This is only good, I'm claiming, for showing a limit does not exist. So how do we compute limits? How do we show they exist? Well, that's exactly like we did in Calc 1. We first prove that some really basic limits exist, and for some particular functions. And then we prove a bunch of rules that allow us to combine those results and get a big class of functions that we can compute limits by direct substitution. That's the idea, is we want to use direct substitution. So let me just say direct substitution. Now these laws I'm going to write down are proved using that formal definition of the limit that I showed you at the beginning of the video. We're not going to do that here. That's usually saved for a real analysis or advanced calculus class. So if you want to go more into mathematics, if you go to grad school for mathematics, you will do that there. But not everyone needs to actually work those out. So what are these? We're going to have three sort of fundamental rules here. One is that the limit, as we approach, let's say, AB, of a constant c is a constant. So a constant function, right? This will just look like a plane parallel to the xy plane, right? That's a constant function for a function of two variables. So here f of xy is just equal to c, constant. Well, if we take a limit as a constant, I don't care where we approach, we get c. So that's one. That's an easy one. And of course, the very nature of these should be really easy. They should be almost common sense, obvious. If we approach the linear function x, so this looks, right, this is f of xy equal x. This also gives us a plane. And when we evaluate this at the point AB, so it's like we're trying to plug A in for x and B in for y, we get A. And finally, what if we're approaching the same point AB, but what if we're now working on the function just y? Then we get B out. So the goal is to now take these very basic fundamental rules and combine them. So now prove rules about how we can combine limits and get a huge class of functions that we now know how to evaluate limits by direct substitution. This is exactly what was done in any Calc 1 class. This is how you build up. So Now we have a bunch of limit laws that again are proved using that fundamental or that definition of the limit of a function of two variables. And so now we get all these rules, right? The sum of two functions, difference of two functions. So if the limit is x approaches a b is L, and for g it's m, then the limit of the sum is the sum of the limits. Limit of the difference is the difference of the limits. Constant multiple multiplied by f, that'll go to c times L. Right? Limit of a product is a product of the limits. Limit of a quotient, limit of a function raised to a power, limit of a function raised to a fractional power. All of these hold, and this allows us to now put these guys together. So if I want to say do the limit as, let's say, xy approaches 1, 2 of, I don't know, x plus y. So it's not one of these that we proved, but it's the sum of this function x and this function y, that this would go to, let me actually not do a particular value. Let me do ab. No, you know what, I'll do 1, 2. No. So this will go to, so this would be a, which is 1. This one would go to b, which is 2 here, and then I would take the sum of them. So this would be 1 plus 2. This would just give me 3. So that's what this allows us to do. We can take products of functions we already know and we build our way up. So we have polynomials now, algebraic functions, things like that. So in the next video, I'll go through an example where we'll evaluate this limit by direct substitution. If you're following along, you should be able to actually do it pretty quickly. It's okay if you can't. I'll do a video for this one, but you know, test yourself. Did you get what I was putting down in this video? And especially at the end, can you figure out what this function, what the limit is as we go to the point 2,8? All right, I'll put the answer in the next video. I'll see you there.